It's weird that this part is a little bit darker. Oh, it looks okay here, right? Yeah. Okay, let's get started. So I first wanted you to explain you what is this eigen thing. Do you know what is this eigen thing when we talk about eigenvalues and eigenvectors? The Eigen is like super popular thing. Right? There's a software library called Eigen, which is a pretty good package for linear algebra. If you ever need to do it outside of MATLAB, Eigen is a good option. There is even a company, Eigenvector. There are Eigenfaces. It's like Eigen everything. Do you know what is that Eigen?
Like a Joe Eigen?
There was a dude called Eigen. Yeah, I think it was even like a Nobel laureate or something like that. But I think it has probably nothing to do with eigenvalues and eigenvectors. The thing is that Eigen is from German. Eigen is a word in German which means like its own or self or unique or characteristic. Remember when I took linear algebra classes in Czech, then this was actually translated. And sometimes you can see like characteristic values and characteristic vectors. That means the same thing. So. And German also has like this funny habit of like creating new words by concatenating words. So this would like also explain why like it's just stick together eigenvalue and eigenvector. So that's a terminological note to what does that mean. And the point is that they were trying to say that this is like something characteristic, something proper, something almost unique to the matrix. Okay. So what are those? What are the eigenvalues and eigenvectors? So they are always like brothers. They will come in pairs, right? There's an eigenvalue and a corresponding eigenvector. So the eigenvalue is this lambda and the eigenvector is v. And this is for a square matrix. Can be real, can be complex, and we will have to go complex here. I will explain that when we get there. And what it means is that the matrix product AV reduces to a scalar vector product lambda v, where lambda is the eigenvalue and v is the eigenvector. So this is just recapitulating definition. An important catch is that the eigenvector must not be 0, right? I was explaining that previously. If v is 0, then this equation is saying nothing, so it's not interesting. So we must disallow this trivial case. Maybe eigenvectors are by definition non-zero. And this is how we find it, and I think I ended by saying that we need to do an example to get you an idea. So let's do this quickly again. This is like super important. Eigenvalues and eigenvectors are super important. Like that's also why this name is so popular. It's why you can hear about eigenfaces and eigenskin and eigenfactors and all these eigen things. And as I said, the PageRank algorithm used by Google also hinges on the properties of eigenvectors and eigenvalues. And it all starts with this basic derivation. So we have a matrix. We are given a matrix A, and we need to find the eigenvalue and eigenvector. Let's say we want to find just one for now. So what we do, we put this on the left-hand side. Here we need to stick in the identity, which is fine, doesn't do anything. And so we conclude that this matrix, we are looking for the lambda and v, and we conclude that this matrix must be singular, must have a null space of dimension at least 1. Okay? That means that the determinant of this matrix has to be 0. It could also have a null space of dimension more than 1, but it has to be of dimension at least 1. So that leads to the determinant equation. Determinant is that's basically why we were discussing determinant before. And you know that if the only variable here is lambda is a scalar here. It could be a complex scalar, and we will do that in a little bit, but we can, for a second, we can assume it's just real. Doesn't matter now. Doesn't matter for this statement. In either way, the determinant, because the only variable here is the lambda, is going to be a polynomial of degree n, right? Because determinant is a sum of products, and these products involve at most n elements from the matrix. So at most, I will hit lambda n times in the product, right? I'm just recapitulating this, what you should already, I don't know if I should say remember, but you should have heard that before. And this is the characteristic polynomial of the matrix, the polynomial associated with this matrix. And the roots of these characteristic polynomials are the eigenvalues. Okay? So let's see, let's do an example. Let's do a 2x2 example. Those are my favorite examples. This chair is pretty cool, by the way. I like it. So let's take this matrix. Just a 2x2 matrix, so the determinant becomes very simple there. And let's say we want to find the eigenvalues and eigenvectors of this matrix. So the first thing we do, we form the characteristic polynomial. So again, remember the general recipe is to take A minus lambda identity. So here is the, so we do it really carefully here, 0.8, 0.3, 0.2, 0.7, minus lambda, 0, 0, lambda, right? So it boils down to this equation. So this is an alternative notation for the determinant. And we set this to 0. We are looking for lambdas that satisfy this equation. So determinant of a 2x2 matrix is simple, right? So you just multiply this one with this one, so it's 0.8 minus lambda times 0.7 minus lambda, and you subtract 0.2 times 0.3. Why there are so funny numbers is that we like eventually end up with nice eigenvalues, but that doesn't matter, it could be whatever numbers. So here you can see clearly it's a quadratic polynomial. If we simplify it, we get here lambda squared, right? So that's the highest order term. That's the highest order monomial there, because and it comes when we just hit the two lambdas there. So that's the lambda squared. Then you have 0.8 lambda plus 0.7 lambda in minus, so it's minus 1.5 lambda. And this one is 0.8 times 0.6, which is 0.56 minus 0.6, which is 0.5, right? So that's the constant term here. So here is our quadratic polynomial. So this is the characteristic polynomial of this matrix. Now the roots of this polynomial will be the eigenvalues. So how do we find roots of a quadratic polynomial? I think you should know that, right? There is this formula. If I have a polynomial ax squared, general quadratic polynomial, this is, I think it's like high school stuff. So the roots are minus b plus minus b squared minus 4ac. I'm actually curious, did you have this at high school, or where did you learn? Yeah? Okay. Yeah. So we just use this formula to find the roots. Like quadratic polynomial, very, very easy, right? It gets harder if you go to higher and higher order. But for quadratic polynomial, everything is very easy. So minus b here is 1.5, and plus minus b squared minus 4ac. So this is the 4 times 0.5. So this gives me that it's 1.5 plus minus, let's see if this is correct, 1.5 squared. Oh god, if I remember. So this is like 3/2 squared, so this is 9/4. So this is like, this is 1.25, no, 2.25. Minus 2 is 0.25. Yeah, so that's fine. It's always good to double check. And the square root of 0.25 of this is 0.5. So I see that the two solutions are, if I do plus, I get 2 divided by 2, which is 1. That's this one. And if I do minus, it's 1 divided by 2, that's 0.5. So here I am lucky. Here I have 2 real eigenvalues, which is nice. So those are the eigenvalues for this matrix. So here you see how it works. Actually, one of your yeah, question.
Is there any like geometric representations of like the eigenvalues or just the vectors itself?
That's a very good question, and there is. it will make more sense when we compute the vectors. So let me finish with the vectors and then remind me if I forget to get back to that. But yeah, there is geometric interpretation. Yes. What I was gonna say. Oh yeah, this is also one of the examples you have in your homework due next Friday to compute eigenvalues and eigenvectors. So this is essentially what is being done there. If it's a 3x3 matrix, the principle is still the same, except that this will be like a third-degree polynomial. You can still find it through its roots. Okay, so these are the eigenvalues, which is just half of the story, the harder half of the story. The other half of the story is to find the eigenvectors, right? So let's see, how do we find the eigenvectors? You should actually know this by now, right? How to find the eigenvectors. Because eigenvectors are the solutions to this homogeneous system, where the lambdas you already know. For the lambdas, we plug in the eigenvalue. So we take one eigenvalue. For example, I take the eigenvalue, what was it? 1 and 0.5. So here I take, let's say lambda 1 is 1 and plug it in. And I need to find a vector which is in null space of this matrix after I have subtracted the eigenvalue times identity, right? It's because I'm solving this. This is the formula I'm solving to begin with. The first step is to figure out what are the eigenvalues. And then for every eigenvalue, I need to find its corresponding eigenvector. For, as I said, they are like pairs, they're like brothers or sisters or whatever. That every eigenvector has its corresponding eigenvalue and the other way around. So the principle is to first compute the eigenvalues and then find their corresponding eigenvectors. So if you already know what the eigenvalues are, then the eigenvectors are solved by solving this homogeneous system. Again, you could just tell me, oh, 0 solves it. But remember, I said that 0 eigenvectors are prohibited because that would always be, that's always true, right? So we need a non-trivial solution of this system. We need a non-zero vector v that solves this. But you should already by now know how to do that, right? So that means that this matrix will be singular. So it means it will have at least one free variable. But we now know how to deal with that, right? The consequence of this will be that there won't be a unique solution for v. Even for non-zero v, there won't be a unique solution. But there will be at least one-dimensional subspace of the solutions, right? I can always scale this v by a scalar, and it will still be a perfectly fine eigenvector, as long as that scalar is not 0, because that would give me a 0 vector. Okay? So how does it work in this example? Let's take a look at that example. So here I subtract just the identity, right? Because the first eigenvalue is 1. And I get this. I get minus 0.2 on the diagonal and minus 0.3 here. And from this, you can see that the two rows are obviously linearly dependent. They have to be because the matrix has to be singular. And from this, you can see that you can just flip it and get a solution. You can just put the 0.3 here and 0.2 here, and obviously you need to get 0, right? So this is our eigenvector. The other way, if you wanted to do it the standard way, you could just say that the second equation you can disregard. So you can like say that minus 0.2 v1 plus 0.3 v2 has to be 0. But then v2 is a free variable, so I can pick there whatever. So I can say, for example, that v2 is 1, which leads me to this. And then I will get that v1 will be 0.3 divided by 0.2, which is 1.5, right? So this way I would get that v is 1.5 and 1, which is also true because it's just a scalar multiple of this, right? Do you know what this means? Proportional, yeah, that means up to scale. So I guess I could also write that v is 0.3, 0.2 times alpha, where alpha is arbitrary scalar except for 0. Same here, right? So if I multiply this by 5, I get exactly this guy. So they are really one and the same eigenvector. So the eigenvectors are unique in terms of the 1D subspace they generate, but not in terms of the vector I choose to represent it. Yeah, that's so that this is summarized here, that the eigenvectors only define up to a scale, and any multiple of v will also be eigenvector with the same eigenvalue. So that's not true, right? We need to say any non-zero multiple will be eigenvector the same, but that's trivial. Okay, so if we do the same thing for the other eigenvalue, we still have the lambda 2 equals 0.5, right? So we do exactly the same thing. We form this matrix 0.8 minus 0.5, 0.3, 0.2, and now 0.7 minus 0.5. And we are now looking for a v that will give me 0. So I'm not gonna do the whole compute. Oh, maybe I could. Doesn't. Yeah, let's. It's trivial, right? So let's just do it. So that's 0.3, 0.3, and I have here 0.2 and 0.2. If you don't get here a singular matrix, something went wrong, right? This must be a singular matrix. That was the whole point of the determinant exercise to begin with. So here you can see that the other, actually let me give it like v2, that this was like v1. Oh shit, now I used the, sorry, the v1 I used also for the coordinate here. So let's re-node this to x. And now it's fine. So the v2 is, what could be v2? The second eigen, so the eigenvector corresponding to eigenvalue 0.5. 1, -1, exactly. Or -1, 1, right? Or 0.5 and minus 0.5, whatever you want. It's again defined up to a scale, right? So this is the good case. This was the easy case. It was nice. We were able to find real eigenvalues corresponding to real eigenvectors, and there is a full number of them. We had a 2-dimensional matrix. So the most, maybe we could. That's the most that's the highest number of eigenvalues, eigenvectors we can eigenvalues we can ever find. Is equivalent to the dimension of the matrix. Okay, so now you can be thinking, okay, that can't always work, right? It would be too good to be true, and it obviously doesn't. If you have a quadratic polynomial like we had here. Of course, there is plenty of quadratic polynomials that they don't have any real roots, right? Oh, yeah, back to your, to your geometric interpretation, right? So now we have the eigenvector. So let me pick, for example, this v1. So if I just draw it like this, so this would be 1.5, this would be 1. So this is my v1, right? And the corresponding eigenvalue was 1, right? So that means that AV1 is v1, right? So that means that whatever the matrix A is doing in a higher number of dimensions that might not be obvious, this vector just stays put. More interesting is the case of v2. v2 was like 1 and minus 1, so it's like something like this, right? 1 and minus 1. This is v2. And what happens to v2? A v2 is 1/2 v2, right? So the matrix maps v2 to its half. So that's the geometric interpretation. These the eigenvectors are the directions which are unchanged by the action of the matrix. the direction as a 1D subspace, when I look at it as a line, the direction stays put. Whatever vector on this line gets mapped by the matrix on a vector on that line. The same is true for the other eigenvector. It would not be true for any other vector in the plane. Those are the special vectors that have this property. And the eigenvalues, then they tell me what is the action of the matrix on this 1D linear subspace. And this action is just a scaling in that 1D subspace. So in this case, in the case of V1, the scaling was trivial, it was just multiplied by 1. But in the case of V2, the scaling is not trivial, then it means shrink everything like this by a factor of 0.5. So that's the geometric or one of the geometric interpretations. There will be even better later on.
So what do you mean by the action of the matrix?
I mean, if I multiply a vector by the matrix.
Oh, okay.
If I do matrix vector, matrix is a linear transformation, right? So every vector is transformed by the matrix to some other vector, right? Most usually I take some vector and it gets mapped somewhere else, right? Like if I have a rotation, then like a vector like this gets rotated to somewhere like this, right? But for certain matrices, so you can see that rotations cannot be it. But for certain matrices like this one, the 0.8, 0.3, 0.2, 0.7, we can find the special directions which are unchanged by the action of the linear transformation represented by this matrix. That's what I mean by the action. Okay? Okay, so as I mentioned, for rotations, we cannot possibly have real eigenvalues and real eigenvectors, right? Because that's just impossible, right? Rotation takes any vector and rotates it. Even if it's rotation by 1 degree or something like that, always takes a vector and rotates it a tiny bit. So it's never gonna be the case that there would be some special directions that would be mapped onto themselves, that would stay on that line, right? Just slightly annoying, but thankfully smart people before us figured out a way to deal with that, and the way is to go to complex numbers, and that's what we will do. That's the standard thing that's done in this case. The problem is that if we have a polynomial of degree n, then we are not guaranteed anything about the real roots, but we are guaranteed from the fundamental theorem of algebra that a degree n polynomial will have n complex roots. So that there it's good. In complex numbers it's great, because if we have a degree n polynomial in the complex, it can have real coefficients, that's fine, but we are guaranteed that we'll have n complex roots. So we will have n eigenvalues, but we have to go to the complex domain. By the way, this fundamental theorem of algebra is a bit of a misnomer. It's neither fundamental nor of algebra, but it is true. Anyway, because it's really like a calculus statement, not an algebra statement, and there is really nothing super fundamental about it. Even though here it's like really useful, because it guarantees us that if we go to the complex domain, we will always be able to find n complex eigenvalues. And sometimes it happens that these eigenvalues happen to be real, but not always. Sometimes we have to go to complex numbers. So here I have a couple slides to just refresh your complex number know-how, no kung fu or whatever. you know complex numbers some, right? So this should be just a recap, I hope. So the motivation is that we cannot always square root, we can never square root -1 in the real domain. So that's why we go to complex domain and introduce this imaginary unit I, which square is -1. It gets even more, complex numbers are actually just the most important example, but certainly not the only one, of like funny algebras that do this. There are also quaternions, right? Which you might have seen in graphics. There are dual numbers, which are another funny algebra like this. But complex numbers are by far the most important of them. So let's take a little bit at their properties, because we will need their properties to then reason about these complex eigenvalues and eigenvectors. eigenvectors. And that's a standard thing in linear algebra. You just have to do it if you want to be able to reason about eigenvalues and eigenvectors already of like rotation matrices. So the complex number in general is just the sum of real part and purely imaginary part, where the purely imaginary part is multiplied by the complex unit, right? And those are just some two complex numbers, and here are the properties. So addition is pretty simple, just add it per component, like the real parts and the imaginary parts. Subtraction, the same story, right? I guess I could also have like multiplication by a scalar, also very simple. Oops, except I can get it wrong given the simple thing. Plus I alpha y 1. Multiplication is a little bit funny. Thankfully, the complex numbers are commutative. It's not written here, but it is true that lambda 1, lambda 2, where lambda 1 and lambda 2 are from the complex domain, is equal lambda 2, lambda 1 for each lambda 1 and lambda 2 complex. So I guess this is true. And the multiplication works like this. You can just like work out. You must have done this before, right? Have you? x2 plus y. I mean, we will not need this a whole lot, but we'll need it a little bit. So if you just like expand this, you will get exactly this formula, right? What am I doing? x1, x2. Then I have, so y squared is minus, right? That's why this minus appeared here. And I have just I, y1, x2, and x1, y2. So this is how I get this formula, multiplying two complex numbers. Now what is really important, what we'll really need is conjugation. So remember this. Conjugate of a complex number means swapping the sign of the imaginary part, right? So if my lambda 1 was x1 plus I y1, then the conjugate is x1 minus I y1. The absolute value, it's like the length of that thing. Like you can also like think about complex numbers as 2D vectors, right? Essentially complex numbers are, what they are is adding some more algebraic structure to 2D vectors. That's one way you can think about it. You define a way to multiply them. But the length will be the same length as of a 2D vector. So you just take x1 squared and y1 squared and take the square root of it. Just like when we are doing dot products, right? You should know this very well. Turns out that this is actually the same as doing the lambda and lambda complex conjugate. Because look what happens. x1 plus I y1. And if I do the complex conjugate here, then it turns out that these guys cancel and I will get x1 squared plus y1 squared. That's because the I squared is minus 1. There's another minus, so it gives me plus. So that's very nice. Right? And these guys just cancel. This is x1 minus y1 minus, and there is one with plus, so they just fall out. So this is sort of neat. It generalizes to quaternions too, and some other algebras. The inversion for every non-zero lambda. So what is a zero complex number means 0, 0, right? 0 real part, 0 complex part. That's the complex 0. Yeah, I can also have like 1 when I'm looking at it as a complex number. That means just this, right? 1 plus 0 times the imaginary component. So this is how I invert a complex number in general. The interesting thing that's just the conjugation divided by the length. So if I have a unit complex number, so unit complex number would be such that this is 1, right? So unit, just like unit vectors, really. So if it's unit, then the conjugation is exactly inversion. And one property we will need for complex eigenvalues and eigenvectors, or to show some of interesting properties there, is that the complex conjugation commutes with multiplication. So it doesn't matter if I first multiply lambda 1 and lambda 2 and then conjugate, or if I first conjugate and then multiply. It's very, very easy to verify. You can do it in like 2 seconds if you want. And also, of course, if I sum things, then it also doesn't matter if I conjugate first. So if I first sum and then conjugate, it's the same thing as if I first conjugate and then sum. Or subtract, doesn't matter. Okay, there's a little bit more about complex numbers. You probably also know this, right? That like I can write every complex number in polar form. You know, have you had this before? That's really because any unit 2D vector I can write in this form, cosine and sine, right? Because that's a unit circle, and the r is just a scaling term. So that's why this works. So the r is really just the length we just defined, and the theta is the angle. I think here it would be better to use like the Eigen2. Do you know the Eigen2 function? It's super cool. That's exactly what returns you for a number x and y. It returns you the angle. What's cool about Eigen2 that it works like no matter where you are in these quadrants. For any y and x you feed it, Eigen2 gives you the correct angle. So if you're like here, that it gives you the correct angle like this. I hope. I think it does. I think it's even defined if both of them are 0 actually. Like the Eigen2 is like really nice if you ever need to do this. So this is the polar form representation of complex numbers. And the last thing I'm going to mention about complex numbers is the complex exponential, because in a little bit we will be talking about matrix exponential, and the complex exponential is sort of like a warm-up to it. So there's the thing called Euler's theorem, which says that the Euler's number raised to a complex number, to a purely complex number, I theta, is actually this. It's just cosine theta plus I sine theta. This can be proven, for example, from Taylor's polynomial, but like I'm not doing calculus here. Let's just take this for granted. Yeah, this is just like a nerdy statement that you can like get this cool equation from this. So if you just plug there pi, then I get the cosine of pi is -1, right? And sine is 0, so I get this equation. But this is just like a nerdy comment. You can pretty much ignore it. But what is interesting is that these exponentials give us interesting way or easy way to do complex multiplication. So if I can take any complex number, I can write it in the polar form, which is, now we know that this cosine theta plus I sine theta can be written also as e to I theta, e to raised to the power of I theta. And of course I can also write r as e to the natural logarithm of r, right? Because the logarithm is just inverse function of exponential, so this is identity. And then if I multiply the two, then this becomes e I theta, so I can just sum them together, and that's what's written here. So this makes complex multiplication easier, because if I convert both of them to this representation, then see what happens. Then the logarithms get summed, and these thetas also get summed. It turns out that if the lengths of the complex numbers are all 1, then this just corresponds to rotations in the complex plane. So this is something interesting, that unit length complex numbers correspond to 2-dimensional rotations. You can sort of see it here, right? This is like a rotation, and if I multiply two of them together, all I'm doing, I just add these angles together. This is, by the way, how you can also like derive very quickly the formulas for like cosine theta 1 plus theta 2 and so on. You can get it from this formula fairly easily, but that's not the point here. The point here is the complex eigenvalues. So let's take a look at this. So as I said, we are not always so lucky that we would get real eigenvalues. Sometimes we just need to consider complex eigenvalues because we are guaranteed that the characteristic polynomial will have n complex roots, and sometimes those complex roots can be real roots, but not always, right? Sometimes we just have to suck up the complexity, so to speak. So let's take this matrix, for example. Let's show it on an example, and this is one of the simplest examples I can think about. So what is this matrix? I think we were discussing it before. What transformation is it doing? Remember, we had rotation. We discussed it before. The rotation matrices. So this is a matrix of rotation. It's carefully chosen so it has nice numbers. It's a rotation by minus 90 degrees, right? Again, the general rotation matrix looks like this. So this is a rotation about minus 90 degrees. So for rotation, as I said, there is no hope we would have any real eigenvalues in 2D. In 3D, it will actually be different. Yeah?
What about you rotate it by like 360 degrees?
Yeah, then it's not really a rotation but identity, right? Yes, rotation by 0 degrees, which is the same as rotation by 360 degrees, or rotation by 720 degrees, and so on, right? Yeah, you're right. That's a special case which has some real, like, yeah, right, correct. But for rotation that is actually doing something, you will not have real eigenvalues. So that's the case of this rotation, right? It's rotating by minus 90 degrees. So let's see what happens. Let's compute the characteristic polynomial. So you know the drill. We are looking for determinant of a minus lambda I, right? So this, I just subtract lambda from the diagonal and compute the determinant of this. So I get lambda squared plus 1, right? You remember the formula for 2 by 2 determinant, I hope. So this is the characteristic polynomial. And there are really no real solutions, right? The graph looks like this. So it's never gonna intersect the real axis. But there are complex roots. There always are complex roots. And in this case, the complex roots are plus and minus I. That's obvious, right? Because both plus and minus I squared, plus and minus doesn't matter. It's just I squared, just minus 1, so this gives me 0. Now the cool thing, that's why I was talking so much about the conjugation, is that this is not just a coincidence that the solutions are plus and minus I, but every time you have a complex eigenvalue like lambda, then lambda complex conjugate is also one eigenvalue. So that's what happened here, right? Because I complex conjugate is minus I. And why is that? It's because if I have my characteristic polynomial p lambda, which is, let's just do the quadratic case, b lambda plus c. So if I plug in the conjugated lambda, it's gonna be lambda conjugated squared plus b lambda conjugated plus c, right? But we know that this is true, and because the A, B, and C are real because the matrix was real to begin with, then for a real number, the conjugation does nothing, right? So I can as well put there, I can as well conjugate A, B, and C. Just because A is a conjugate, that means that A is real. A is real if and only if it's equal to its conjugate. And then from the properties of conjugation, I can just put it all together. So this is just this entire thing conjugated, which is just a sign of me running out of space, but this just means that's P lambda conjugated. So if this was 0, this is going to be 0 conjugated, but doesn't matter, it's still 0. If that was 0, if lambda was an eigenvalue, then lambda conjugated also is an eigenvalue. So that means that the eigenvalues always come in complex conjugate pairs. Right? Like here, I and automatically minus I also is an eigenvalue. So they are always in pairs, which is cool. Like that's the cool thing about algebra. It like gives you all these clues to solve these mathematical puzzles. So that also, from this we can derive a cool thing about a rotation in 3D. If we have a rotation in 3D, or really any matrix in 3D, it must have at least one real eigenvalue. Right? Because why? Because we will have 3 complex roots, right? But they must come in complex conjugate pairs, right? So at most there will be one complex, because if there were two different ones, we would have to have 4, but that's impossible. So in general, for an odd degree polynomial, we are guaranteed to have at least one real eigenvalue. But anyway, this what is the main point here is, so we have computed so far the complex eigenvalues, and we still need to compute the corresponding eigenvectors. So one thing to realize is that once we had to go to complex eigenvalues, there is no hope that the eigenvectors could be real, right? We are multiplying a complex number with it. So we need to go to complex eigenvectors as well. So here we are working in the vector space C to n as opposed to the R to n, which we were working with before. But it's fine because everything still works. It's just a vector space over a different field. This time it's not over the field of real numbers as we are mostly using, but over the field of complex numbers. But it's okay, it's not such a big deal. So like here, so we need to find now the eigenvector corresponding to the eigenvalue, for example, I, the first one. So we do it exactly the same way as before. We take the matrix and subtract, so we do the A minus I identity, right? Where I substituted the I for the lambda, so that's this matrix. And you can see that's again linearly, it's a complex matrix now, but that's all right, you have to deal with it. And it's fairly easy to see that one solution will be minus, so again, what we are, let me go a little slower. What we are doing, we are looking for a non-trivial solution to this homogeneous system, right? We need to find a non-zero, it still has to be non-zero, even if it's complex, must be still non-zero. But now it's allowed to have complex numbers. Now we actually need to have complex numbers, otherwise we would never satisfy that. So one solution is minus I and 1, because if I do minus I times minus I, that's the same as I squared. That's minus 1 plus 1 is 0, right? And this is just a linear combination of it. This is just multiplied by I. So this is our corresponding eigenvector. Now it has complex entries. Now the geometric interpretation here is a little elusive. I actually don't know what is the geometric interpretation of these complex things, and I didn't find one in Gilbert Strang's textbook either. There might be something going on, but it's like really hard to imagine what that really means. But it doesn't matter, the algebra still lets us work with this. Now one thing we can work out immediately is So for the other eigenvalue minus I, we would repeat the same procedure and we would get a different eigenvector, right? So this is the eigenvector I1 is the eigenvector that corresponds to minus I. And of course, I can still be scaling these guys by a scalar. This time it can be a complex scalar. I can scale it with, and will be still this not the same eigenvector, but the eigenvector corresponding to the same eigenvalue. Now, one thing we can immediately realize is this. So if we know that this is true and these things are complex, so V is a complex eigenvector and lambda is a complex eigenvalue, but A is a real matrix to begin with. So it turns out that if I take the complex conjugate eigenvalues, we know for every eigenvalue this complex conjugate is also an eigenvalue, and the corresponding eigenvector is also going to be complex conjugate. That's because if I do this, lambda complex conjugate times V complex conjugate, I will get lambda V, this whole thing conjugate. But lambda V is just AV, right? So this is just AV complex conjugate, which is just A conjugate, B conjugate. But A is real, right? So A conjugate is just A. So this proves that V conjugate is an eigenvector corresponding to the eigenvalue lambda conjugate. So that's nice because we know that the eigenvalues come in complex conjugated pairs, and their eigenvectors are also just like conjugates of each other. They are like brothers again, or sisters to be politically correct. And you can see this here, right? This was the case here. If I conjugate this guy, I get exactly this. Okay. Everybody sort of happy about this? Okay. So then one application, there is like a zillion application of eigenvalues and eigenvectors, but one basic one is matrix diagonalization. Or actually even more basic one is like computing powers of a matrix. Or actions of a power matrix. So one like way you can think about eigenvalues and eigenvectors is one of their benefits is that they make matrix vector multiplication very simple and very computationally cheap, which can be important in some contexts. For example, if I have an eigenvector V and eigenvalue lambda, and if I need to apply A twice, then what does it really do? The first application just gives me lambda V, and the second application just results in lambda squared V. Right? So in case I need to compute A to power of k, where k can be like 1,000, it would be real stupid if I was computing A times A times A times A 1,000 times. Right? Because if I know that V is an eigenvector with eigenvalue lambda, all I need to do is raise to the power just one scalar. Right? So if you ever need to implement something like that, then obviously this is like so much faster, right? Here you just take one scalar to a power as opposed to taking matrix to a power. And it turns out that in the special case where we are happy and the matrix has real unique eigenvectors, it has a full set of linearly independent real eigenvectors, we can find this diagonalization. It would also be true for complex, but it would be like a complex diagonalization. So we will avoid that. The discussion of the complex case is really similar to the real case. And this, I think I will need to discuss on Wednesday, because this takes a little bit of explaining. So was it clear so far? Any questions? Okay, so more, stay tuned, more coming up. Thank you.